Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistor, a physics perspective. We will be working on lecture number 56, which is 3-5 HEMT and its modeling. We will start from where we have left in our previous discussions or previous lectures. Typically when you do a model, there are multiple types of modeling techniques available, both for HEMT as well as for any other devices. For any structured devices, you can have analytical model, right, which is basically a physics based, which are basically derived from first principles of physics. Second are empirical models. Empirical models are sort of models which are developed from experimental analysis. So you don't know anything about the devices. You take an experiment, prepare an experiment, plot a graph, and then from the graph you try to extract the numerical relationship between y axis and x axis. That is sort of an empirical model, and you try to tune it by putting certain fitting parameters within the empirical or empirical constants, so that the simulated line and the experimental line matches with respect to each other. So it's one of the easiest way to do it, but then for this you require a very standard and repeatable experimental work to be designed. Analytical model, whereas, is basically physics based model, which are basically from first principles of physics. They try to do it. Certain assumptions are taken in analytical model, and therefore they are relatively sort of faster in nature. Next is basically what is known as a numerical model. So numerical models are again relatively, you don't take any assumptions to a larger extent in this case, and you try to solve the equations in a numerical fashion, right. Now, so these are the three typical models which traditionally has been used, but however, with the advent of machine learning and artificial intelligence, machine learning based models have also picked up a pace, because if you have a heavy database available with you regarding a particular experimental data, you can actually formulate a machine learning based model. So HEMTs, all FET devices also have machine learning based models available to us. Now, if you look at the timeline, typically 1980s, if you look at the left hand side of this design, this 1980s early model were based on empirical models, and this was done. One of the model which was done was basically the Stats and Curtis model, which was developed. Now, in this, the earliest empirical model was ascribed to the fact that empirical models used a relatively simple expression. So empirical models actually used relatively very simple expressions, and you don't have to worry about the expression itself, right. Simple expressions were used. The empirical models were used. Now, some representative empirical models, as I discussed with you, as also written here, is Stats and Curtis model is available. You did have an Angelov model which was developed around 1990s and early 2000. He had what is known as an Angelov model, right. Now, these Angelov models have been modified large number of times in recent times. So these modified, as that's what is written here, that we have got these modified Angelov models being attached, and these Angelov models or modified Angelov models is generally used in many of the current generation HEMT model designing of HEMT models. Some there is another model which is known as an EEHEMT model, right. EEHEMT model which is being developed, and these empirical models mainly appear in 1990s. However, they still remain there, that they are quite valid even today, because you do have large amount of experimental data to support these models. The empirical models exhibit of being very accurate, and they are easy to use, highly tunable. So empirical model also is relatively more accurate, right, and they are tunable in terms of application. And then third thing is they are relatively easy, easy and simple to actually design. So these three things sort of makes an advantage for the formulation of these for these model, and they're relatively accurate as well. Uh, okay, there are many machine learning based gallium nitride, machine learning based GAN HEMT models, right, which have come up, in which we use ANN, artificial neural networks based GAN HEMT models, and these have appeared around in somewhere around 2000. So sometimes around 2000, these ANN based models, machine learning based models, have actually come up in a big way, right? And still they are being used in many of the cases. Being the advantage of having one is that it is ANN based models are naturally capable of accurately predicting the device's nonlinearity very well, right? You can catch up with the device's nonlinearity very well using ANN techniques, and which becomes difficult when you do primarily other methodologies. You do some amount of approximation. Here you don't do too much amount of approximation, and therefore the accuracy is not being sort of sacrificed in a sense. Therefore, due to the strong fitting ability and low deployment. So where do you use it? ANN has got an advantage, that low deployment cost, because if you have data available with you, and it is relatively easy to handle ANN. So with low deployment cost and more accuracy, they are being used. Then one well-known model which was developed was known as a DynaFET model, and this was developed by Keysight, right? In about in 2010s, somewhere around 2010, the Keysight of the device was found. Then advanced SPICE model, ASM HEMT model was also developed. Advanced SPICE model was developed, which was there. And then MIT virtual source HEMT model. This was MIT's virtual source HEMT model was also developed. And then we had a HISIM model, which is Hiroshima University Stark IGFET model. IGFET is insulated gate field effect transistor model. So this was the HISIM model which was developed. These are all high power models which came up. Then we have EPFL model of gallium nitride based HEMT devices also came into picture. And these all happened between 2010 to 2020, 21, 22. Around this whole era of one decade, you have these models being developed, and these physical models are based on certain rigorous physical equations, right? They are typically robust and scalable as well, right? And this is one of the advantages which is being used here. Now, we also, over a period of time, there were two areas in which, for any circuit simulation purposes, it was the whole model was divided into two parts, right? The first was the intrinsic part, the transistor itself, and then you have the extrinsic elements, which basically construct the contacts, right? External contacts and so on and so forth. So typically, if you look very carefully in these model files, you will see that I've already discussed with you the line within the dotted structure. This is my intrinsic transistor. So this is my intrinsic transistor consisting of the HEMT, and these are my equivalent circuit values. So for some capacitances, resistances and inductances, they typically form the extrinsic material, right? And the intrinsic transistor is the driver of the whole device. So basically the GAN is divided into this part, and then you have these extrinsic elements being attached to it, right? And these extrinsic elements need to be modeled. So most of them are typically passive elements, and they need to be modeled properly in order to generate the better model parameters here. Now let us come to the modeling strategy which you do for a typical GAN model. For any GAN model which you do, the typical strategy which you follow in case of GAN or gallium nitride based modeling for any GAN. So we can have a GAN HEMT or a GAN device itself, any other GAN device, power device. So typically what we do is that typically we do characterization initially. So we take up the device, do a characterization, for example a CV meter, try to extract the S parameter of the device, try to see a static and a pulse IV, current versus voltage characteristics, and then we try to fit the models which I have already discussed with you in the previous slide with these characteristics, right? And so we need to find out the appropriate model which sort of fixes with the characteristics which is available to us. So you see that you do this one here in a detailed manner. Then what you do is that you do a parameter extraction using ICCAP and ADS, right? Parameter extraction primarily means that you are extracting various uh, various low level parameters of the device itself, right. Say for example, you want to extract the threshold voltage, or you want to extract the mobility of the characteristics, you want to extract the R on resistance, you want to extract the breakdown voltage. Those are extractable by using ICC CAD and ADS, right. And you do have characterization facility available, you can actually character output it. Then what you do is you try to validate the model which you have actually been formulated by either Angelov or ANN based design using parameter extraction. You try to validate that model with the TCAD or any other data. Now once you have done that and you see there is a mismatch between the experimental and the analytical model, you do a fine tuning or optimization of the parameters. That is what the loop is all about. So this loop which I am talking about here is what the loop is all about. That once you do a model validation, you do this, you come to model validation, and you can see there is a difference. Do optimization and tuning of the parameters, again you go back to parameter extraction, you follow this loop till a time that the difference between them is relatively small, and an accurate result is therefore predicted in the output. Once you have done that and you are sure that these two graphs, these dotted and these lines, are very close to each other, then we directly go to, if required, you can do an advanced testing. For example, pulsed RF measurements, you can do time domain digital modulation, you can do. And finally once that is done, you then form the acceptable model, the model is acceptable. So this is a general trend for this thing. Now you see there are two lines which is being shown here, this one and this one. So what you do is that even when you do very advanced level of testing, those datas are also fed back into the appropriate model and fine tuning of your parameters, so that you are able to achieve the uh, the the accuracy required in a very small amount of time, right, at the cost of doing some higher level experiments for example advanced testing for load pull experiments in a larger manner. And then the acceptable model results are generated, which can be run on multiple data, on multiple bias conditions, on multiple values of other conditions, right, and then you can actually strategize the model. Now within the GAN modeling, if you look at Curtis or even Motorola, BSIM, CFET, HEMT, right, if you can see, typically the number of parameter for BSIM SOI is very large, right, and it uses electrothermal RTS CTH model. Electrothermal means both the electrical characteristics as well as thermal characteristics are taken care of, because you understand thermal, why, because they are operating at such a high voltage and current that the thermal characteristics also needs to be evaluated, extracted and evaluated, right. And then scalability is already inbuilt within the BSIM SOI model, and typically the original device it was using was SOI MOSFET. SOI is silicon on insulator MOSFET, which was used to a larger extent. However, if you go for HEMT, Angelov GAN and Auriga, these 4 or 5, they are all explicitly for HEMTs, right. But some of them unfortunately do. For example, HEMT does not do a full electrothermal model. So that is not an acceptable one when you do when you try to find out a hotspot typically in a 3-5 GAN modeling, whereas others give you the electrothermal modeling to a larger extent. The cost you pay for it is that when you don't do electrothermal modeling, the simulation times are much reduced, right, and therefore if you are doing a first run of the system, it becomes much easier to handle if there is no electrothermal model inbuilt within itself. Geometrical scaling, when I say, is that that scalability of the model. So if you are working with a 3 micron transistor, if you reduce it to 2 micron or 1 micron or 0.5 micron, do the physical changes which appear in the device gets reflected onto the model itself? If it is so, then the geometrical scalability is always referred to, right. So this is a basic sort of sort of existing models which are available for GAN method. Now, I have already discussed with you that the compact modeling based are table based, which is basically lookup table, empirical models, machine learning based model. The physics based models are divided into two parts. One is the threshold voltage based model, another is surface potential based model, right. So there are two ways of doing the physics based model in this case. Now, the one important point which I have not discussed in the previous wave is how do you extract the parameters, right. For example, how do you extract, so say for example you take a silicon MOSFET and you are told to design to extract the threshold voltage. So what you will typically do is that you will plot drain current versus the gate voltage, and then if I plot it in the scale like this, it goes like this. So what we do is that we scale it backwards where it cuts the VGS. This is your threshold voltage, right. This is a linear extrapolated method of extracting the threshold voltage. So this is one of the methods of extractions. So when we say that the parameters needs to be extracted, there are certain techniques available, and these techniques are written here. One is the traditional cold condition extraction. The cold condition basically means that you don't give any biases, right, and external biases are all gone to zero, and what we try to do is that we extract information in that formulation. How do you extract resistances? If you remember, basically voltages and currents, V by I will give you resistance. So just take a two-port network, insert the value of voltages, see the currents through the network, and you can extract the value of resistances. Uh, there are other structural based extractions. I will not go into details of that, but extraction methods for all novel devices are also coming up in a big way when you do a parameter extraction in case of device modeling. Now, let me come to the empirical Angelov model, which is for the gallium nitride HEMT based model, and it was developed in 1996 to 99 by one of the authors, Dr. H.O. Angelov, and the model was developed based on Starr and Curtis model. So the initially model was by Starr and Curtis, and it was later empirically changed by Angelov based on certain measurements. Angelov model adopted independent current source and capacitance sources. So you have independent current sources and you have independent capacitance sources, and using those tunability he tried to find out the value of IDS, or the drain current. So if you look at this expression here, is one of the Angelov empirical model which you see is IDS equals to IPK 1 plus tan hyperbolic sin hyperbolic psi 1 plus lambda VDS tan hyperbolic alpha times VDS, where alpha is basically it basically tells me, governs the transition from linear to the saturation region, and lambda is a channel length modulation parameter exactly in the same manner as you have studied in a bulk MOSFET, and IPK is the maximum drain current at the maximum transconductance point. Now, just like any FET device, MOSFET also HEMT also shows the variation of transconductance with respect to VGS, right. And when this happens, you need to extract that value of drain current at which you get the maximum transconductance, and that is shown by IPK, right. Psi is basically the expression which you see in the last line, right, and it depends upon these factors. So if you look very carefully, if you neglect these two terms, this is a linear dependency of between psi and VPK. So VPK is that value of voltage at which you get IPK, maximum current, and Vg minus VPK is the difference in that voltage which you give, where P is basically a tuning parameter. Now this psi value, if you just neglect these two expressions here, then psi value happens to be a sort of a linear function of the voltage applied, right, VGS minus VPK. But you take the second and third term, then you have a parabolic and a cubic sort of relationship between psi and VPK. So that takes care of the nonlinear part of the current flow which is happening here. So if you feed this value of psi, and if you take this value here and start feeding it at this particular point, you start getting the value of IDS, the drain to source voltage, for various values of VG, right. And that's from here we can extract the threshold voltage of the device itself. right? This is for the HEMT model, which I am trying to say when you are doing an empirical Angelov model. As I discussed with you, Angelov model actually uses a nonlinear gate to source and gate to drain model, and they are expressed in this manner. Don't worry about the expression, actually it's taken from certain research paper which is shown here. And then CGD and CGD and CGS are taken in this manner. Looks complicated, but when you will actually do it on a MATLAB platform, becomes relatively easy to handle this. And these values are all tunable parameters, right? For example, CGSO is not a tunable one, alpha GS is a tunable parameter, and so on and so forth. Uh, advantage of Angelov model is its nonlinearity, that it is able to predict the nonlinear nature of the model, right? And if you look at the right hand side here, this shows the current versus current versus drain voltage relationship, and as you can see, it goes to a maximum value here, and then it starts to fall down as VDS becomes larger and larger, right? Similarly, if you plot ID versus VGS, then at 0 voltage you will have some value, but as the value of the gate voltage increases, it goes on increasing. So this is the measurement and model values taken together, right? And this is from, I think, 4 volts to 30 volts at a step of 2 volts. The measurements has been done, and they have been formulated the current value. And here it is from -2 to +2, the step of 0.2 volts, the values are done, and you can see that the measured value, the model values match with these things. Now, what are the challenges? One challenge is, since Angelov model has got very large number of tuning parameter models, about 90 parameters, and they might not be necessarily independent models, independent parameters. They might be related parameters, right? And what might happen therefore is that that you change one unknowingly, the other also gets changed, right? The second thing is, though CGS and CGD models are nonlinear in nature, but other nonlinear characteristics are not able to be properly captured by Angelov model. Similarly, higher order harmonics problem or ringing problem which happens in power circuits are not captured by Angelov model to a larger extent. So that's the one problem area or challenges which people have in the Angelov model. Okay, before so just let me quickly take up this last model before we finish off, and this is a physical MVS model which we look at. This is a sort of a virtual source model, right? Modified virtual source model which is developed. It's a charge based model. So basically, just like MOSFET, this was basically based on the amount of charge being accumulated within the device itself as a function of the biases, is what you get from the MVS HEMT model. And it very well captures the 2D electron gas property. However, the physical model do not have independent drain current submodel and capacitance submodels. So the physical model, unlike the Angelov model, doesn't have direct IDS relationship. Instead, the drain current equation and capacitance equations are sort of interdependent on each other. So if you look at the drain current equation, it gives me W into NGF into QI into Vx, almost like a standard FET device, where W is the width, QI is the inversion charge density, V is the saturation velocity, and NGF is the density function which you see. And if you multiply all of this, you get ID as the drain current which is flowing through the device. Now, if I assume that the carrier mobility is mu and psi x is the potential at the corresponding point, any point within the channel, and then obviously velocity of the charge carrier will be mu times Ex, because mu equals to V upon E, and therefore V will be mu into E, and E can be written as d psi dx, because electric field is nothing but a rate of change of potential with respect to x. So IDS can be written as W into NGF QI, this thing, and the last term Vx is replaced by this quantity, that mu times d psi x dx. So if you are able to predict how the surface potential is varying with respect to x, and you assume that the mobility is constant for all practical purposes, and you are able to calculate the value of Qi, then you could be able to predict the value of IDS. Now, if I assume that the velocity is saturated, then this was the formula which velocity saturation is being considered, then we considered this to be as the expression where beta is a fitting parameter. V sat is saturation velocity, mu is the low field mobility which you get, right, and it therefore depends upon how does the current flow in a velocity saturated condition case. Now, since I told you in the very starting of this model is that this charge is basically is a charge based model which you see, right. In the charge based model, if you see, so what we do a charge partitioning technique here, just we do in a bulk MOSFET, and we divide this into source charge and the drain charge. The source charge is given by the first expression, which is given by this, and it is given, this is given by the drain expression is given by this, right, and this value of CGS and CGD is given by del Q del V of that particular point. So, if you are able to extract the value of QS and QD, and you are able to see how these QS and QD will vary with respect to the applied biases, I would be able to predict the value of CGS and CGD. So, unlike the Angular model here, the model which you are formulating is coming from the analytical approach which you see. The problem with this model is extracting the values of exact values of the charge partitioning and the source and drain side, right. That is the problem area which you will always face numerically as far as this technique is concerned. So, with this we have finished two types of model. In the next class we will take up the third model and finish off the modeling of GAN HEMT. So, what we have learned in this lecture is we have learned to recapitulate the whole thing. What we have learned is we have learned how the model in a GAN device flows, what is the structure of modeling of a GAN transistor, what are the various types of models available for GAN HEMT, what are the challenges of each of the model, at least the two models which we have spoken, and basic formalism of these models have been shown to you. In the next class we will take up the last part of the GAN model, and we will try to finish off the next part of the GAN model and HEMT model together. Thank you for your patient hearing.